Welcome back to the deep dive. We are doing something a little different today. Usually we look at a specific historical event or an industry trend, but today I actually want to look at a physical object, or I guess rather a system that I think we are all dangerously complacent about.
Oh, yeah, absolutely.
I mean, I'm talking about the light switch.
Right. It is the ultimate background technology, isn't it?
It is, but that's the whole problem. We treat it like magic. I walk into a room, I flip a switch, and light happens.
Yeah.
Instantaneously. But I've been reading through this stack of engineering papers and grid analysis reports, the historical documents you sent over, and my main takeaway is that magic is just the wrong word entirely.
Yeah.
Violence might actually be closer.
Controlled violence. Absolutely. Yeah. I mean, if you look at the physics involved, it's astounding.
Right, because the sources describe the power grid not as a network of wires, which is how I've always pictured it, like a roadmap of cables spreading out, but as a single machine. And I want to make sure I'm interpreting this correctly because it sounds metaphorical when you first read it. Are they saying it acts like a machine or it is literally a machine?
Yeah, it is physically one machine. That is the fundamental concept of what we call the synchronous grid. If you look at the North American grid or the continental European grid, every single spinning part is locked together.
Wow.
So a steam turbine spinning in Lisbon is magnetically locked to a generator all the way in Warsaw. If the machine in Lisbon slows down by even a fraction of a revolution, the machine in Warsaw physically feels it. They have to move in lockstep.
So it's essentially a single drivetrain stretching across an entire continent.
Exactly. It's a drivetrain that spans thousands of miles, weighs millions of tons, and is spinning at a very, very precise speed.
And that speed, the sources refer to it as the heartbeat, the 60 cycles per second here in the US or 50 in Europe.
That's the pulse. And the scary part, which we're really going to get into today, is that this pulse isn't just a digital clock or some software signal. It is the physical rotational speed of the metal itself.
Right.
If that speed deviates, say if that heartbeat drops from 60.0 to 59.5, we aren't just talking about flickering lights in your living room. We are talking about the machine tearing itself apart.
The sources literally call it extreme engineering. And frankly, just reading about the margins of error here, it's terrifying. We rely on this rotational harmony to keep modern civilization running, but the physics keeping it stable are surprisingly fragile.
It's a high wire act for sure. And the safety net keeping us from falling is something called inertia.
Right. Instantaneous inertia. This is really the core theme of the deep dive today. I want to unpack this because inertia is one of those words we use in corporate meetings, like corporate inertia to mean slow to change. But here we are talking about Isaac Newton.
We're going right back to basics. Newton's second law of motion.
The sources use a bicycle analogy, which I usually hate. I hate simple analogies for complex grid engineering, but this one actually clicked for me.
It really is the most accurate way to visualize it. Because imagine you're riding a heavy steel bicycle on a perfectly flat road. You pedal hard to get up to speed, say 20 miles an hour.
Okay.
That 20 miles an hour is your operating frequency. That's your 60 hertz. Now stop pedaling.
You don't just stop moving immediately.
Exactly. You coast. Why? Because you and the bike have mass and you have velocity, you have stored kinetic energy. That energy fights the friction of the road and the air resistance to keep you moving forward. And the heavier the bike, the further you can coast.
Okay, so applying this to the continental grid, the bicycle is the generator.
The bicycle is a 500-ton steam turbine spinning at 3,600 revolutions per minute. The amount of kinetic energy stored in that rotating mass is absolutely colossal.
So this physical inertia acts as a buffer.
Think of it as a mechanical shock absorber. Because in the electrical system, supply and demand must match perfectly every single millisecond. If you turn on a light, a power plant somewhere has to generate that exact amount of extra juice right then. But mechanical systems are slow.
Right. It takes time to boil water.
Exactly. It takes time to open a steam valve. It takes time to burn more coal or natural gas.
But the light turns on instantly. It doesn't wait for the coal.
And that is because of inertia. When you flip that switch, you are essentially grabbing the bicycle and slowing it down. The generator uses its stored momentum, its coasting power, to fill the electrical gap for those first few crucial seconds while the physical fuel systems catch up.
I want to dig into the math here for a second because the research highlights a very specific variable, h, the equivalent inertia constant. It sounds like abstract physics, but the engineering notes suggest this is actually kind of like a fuel gauge.
In a way, yes, but it's not measuring gas in a tank, it's measuring time.
Time? How does a mass constant measure time?
Think of it this way. H represents the ratio of the stored kinetic energy in the rotor to the rated electrical power of the generator. The unit it's expressed in is actually seconds.
Oh,
So
okay.
it answers a specific question. If you cut the steam supply instantly to shut the valves completely, how long can that massive spinning rock keep the grid running at full power before it grinds to a complete halt?
So if a given generator has an H constant of, say, 5
It
seconds.
means that at full load, you have exactly 5 seconds of stored energy in that rotating mass. That is your buffer. That is literally the only thing standing between a stable grid and total systemic collapse while the automated governors try to open the valves and get more steam flowing.
That seems incredibly short. 5 seconds.
It is short, but in the world of electricity where things happen at a significant fraction of the speed of light, 5 seconds is an eternity. It is enough time to save the world, essentially.
Let's make this real for the listener. I want to walk through the journey of a light switch timeline from the sources, because I think we all have this huge misconception that when we flip a switch, we are signaling a computer to send us power.
Yeah, that's not what happens at all.
So I'm standing in my kitchen. I flip a switch for a standard 100-watt bulb. We are going to freeze time. What exactly happens in the window from 0 to 0.01 seconds?
Instantaneously, you close the circuit. A transient electromagnetic wave, basically a surge, races out from your house through the local wires. It travels at about 80% the speed of light.
So practically instant.
Yes, but here is the key thing. At 0.01 seconds, the power plant hasn't reacted yet. It doesn't even know you exist. The energy to light your bulb for that tiny fraction of a second actually comes from the electromagnetic fields already sitting in the local distribution transformers and the wires themselves.
Okay, so the signal is racing out. Now we hit the 0.01 to 1 second window. The surge actually hits the generator.
Right? It reaches a turbine maybe 200 miles away. Now remember the bicycle analogy.
Wow.
You've just added a tiny bit of friction to the tire. The electromagnetic field inside the generator physically grips the spinning rotor tighter.
I want to understand this grip because it's magnetic, right? It's not a physical brake pad clamping down on steel.
It is magnetic resistance. When you draw current, you create a magnetic field in the stator that opposes the rotation of the rotor. It's like dragging your hand against a spinning wheel. So that 500-ton steel shaft actually physically slows down.
So if I'm understanding this correctly in that first fraction of a second, I'm not asking the power plant for more fuel. I'm actually physically slowing down a turbine 3 states away.
You are stealing its speed. You are transmuting its kinetic momentum into light in your kitchen. The coal hasn't burned yet. The steam valve hasn't opened yet. You are running purely on the inertia of that rotating steel.
That is heavy. I mean, literally and figuratively, I'm physically interacting with a massive machine hundreds of miles away just by turning on my kitchen light.
You are absolutely part of the drivetrain.
Oh.
And because you slowed it down, the frequency of the entire continental grid drops by a microscopic amount.
And that drop is the actual signal.
Exactly. The control system on the turbine sees the speed drop and says, whoops, we're slowing down. Then it opens the valve. Then more steam hits the blades. Then we burn more fuel to get the speed back up to 60 hertz.
But that initial moment, that's just me and the steel.
Just you and the inertia.
So we've established that this machine has a pulse. 60 beats per second here in North America, 50 in Europe. I've always assumed this was some fundamental constant of nature, like the physics of electricity dictate that thou shalt oscillate at 60 hertz.
It would be really convenient if it were derived from the speed of light or the golden ratio or something, but no. The sources are very clear on this. It is completely arbitrary.
It's basically a VHS versus Betamax situation.
Worse, it was the Wild West. If you go back to the 1890s, there were frequencies all over the map. The historical notes list systems running at 133 hertz and others all the way down to 16 2/3 hertz.
Wait, 16 hertz? That's barely a hum. Why would anyone build a power grid that slow?
It really depends on what you wanted to power. This is the crucial context for that era. In the early days, you had 2 main applications for alternating current: lighting and motors. If you want to run a primitive electric motor, low frequency is fantastic. 25 hertz or 16 hertz provides massive torque and efficiency for those early heavy-duty industrial designs.
Okay, so why not just use 25 hertz for everything and call it a day?
Because of the light bulbs. At 25 hertz, an incandescent light bulb flickers noticeably. Your eye can catch the dimming between the cycles. It's like being in a strobe light disco. It would drive people completely insane in their homes. To get a steady, pleasing light, you need high frequency, like 100 or 133 hertz.
So you have this fundamental conflict. Heavy motors want low frequency, and residential lights want high frequency.
Exactly. And there was absolutely no compromise at first. Coventry in England actually ran an 87 hertz system until 1906. Just a completely random number that happened to work perfectly for their specific local setup of factories and streetlights.
So how did we actually settle on the 50-60 split that runs the world today?
Corporate warfare, essentially. In the U.S., it was Westinghouse versus General Electric. Westinghouse had licensed Nikola Tesla's AC patents. Now, Tesla was obviously a genius, and he calculated that 60 hertz was the perfect Goldilocks zone. High enough to stop the light bulbs from flickering, but low enough to efficiently run his new induction motors.
So Tesla picked 60.
And because Westinghouse won the really early high-profile contracts, specifically the massive Niagara Falls hydroelectric project, 60 hertz became the de facto standard in North America. GE actually started out pushing for 50 hertz, but they eventually switched to 60 just to be commercially compatible.
But Europe went with 50. Why the difference?
AEG, the massive German electrical conglomerate. They looked at all the same engineering numbers, and according to the historical notes, they chose 50 simply because it was metric friendly.
You're kidding, because it's a round number.
It fits the 1, 2, 5, 10 sequence used in the metric system. It just looks nicer on a data sheet. That's really it. It wasn't superior physics. It was better aesthetics.
And that aesthetic decision from 1890 is the entire reason I can't use my American hairdryer in a London hotel today without it catching fire.
And it has huge ongoing engineering implications. To generate 60 hertz, a standard two-pole generator must spin at exactly 3,600 RPM. To generate 50 hertz, it spins at 3,000 RPM. That 600 RPM difference changes the physical stress on the turbine blades, the size of the machine, the metallurgy. Everything has to be engineered differently.
Speaking of the machine itself, I really want to talk about how these parts actually connect. We said magnetically locked earlier, but I want to visualize the actual mechanism. The outline talks extensively about a magnetic spring.
All right, this is the glue of the grid. It's so important to understand that inside the generator there are two distinct magnetic fields.
The rotor and the stator.
Exactly. The rotor is the massive spinning electromagnet in the center connected to the turbine shaft. The stator is the stationary outer tube of copper coils surrounding it. When the rotor spins, its magnetic field sweeps past the coils and induces an electrical current in the stator. But, and this is the Physics 101 part we always forget, the resulting current flowing through the stator creates its own secondary magnetic field.
So you literally have two massive magnets interacting with each other inside the casing.
And opposite poles attract. The north pole of the rotor's magnetic field is fiercely attracted to the south pole of the stator's field. They desperately want to line up perfectly. That invisible attraction between the spinning part and the stationary part is the spring.
So when the grid is running smoothly late at night with low demand, they are perfectly aligned.
Roughly, yes. But here is where the spring analogy is just perfect. When you add load to the grid, when everyone wakes up and turns on their appliances, you're asking the stator to push more current. That strengthens the stator's magnetic field, which makes the rotor physically harder to turn. So the rotor starts to drag. It lags slightly behind the rotating field of the stator.
It's physically stretching the spring.
It is stretching the magnetic bond. This physical separation between the two magnetic poles is called the load angle. The more power the grid demands from that specific generator, the wider that angle gets.
And just like a real mechanical spring, if you pull it too far,
It snaps.
the outline mentions the math here. It says torque is proportional to the sine of the angle. Why does that specific trigonometric function matter to the safety of the grid?
Because a sine wave is a curve that goes up and peaks exactly at 90 degrees. That means as the load angle widens from 0 to 10 to 40 degrees, the magnetic holding force, the torque, gets stronger and stronger trying to pull it back. It fights you. But once you hit 90 degrees, you're at the absolute peak of that holding strength.
What happens at 91 degrees?
The force drops off a cliff. The sine curve goes down. The magnetic grip suddenly slips. In the industry, this catastrophic failure is called slipping a pole.
And physically, what actually happens to the machine in that millisecond?
Total violence. The rotor is suddenly no longer locked to the frequency of the grid. Because the resistance is gone, it accelerates wildly. But as it spins faster, its magnetic poles pass the stator's poles out of sync. So north suddenly repels north, south attracts south. You have these massive alternating pulses of attraction and repulsion hammering the machine dozens of times a second.
It's vibrating, shaking.
Shaking isn't a strong enough word. We are talking about transient forces of millions of newtons. It's like the entire rotor is being hit by a freight train, then violently pulled in the opposite direction by another freight train, back and forth 60 times a second. It physically twists the giant steel shaft. It can literally rip the massive generator tie-down bolts straight out of the reinforced concrete floor of the power plant.
All because that invisible magnetic angle got too wide.
That is exactly why grid operators obsessively watch the load angle. It is the direct measure of exactly how close you are to the cliff edge of destruction.
Let's talk about the hardware itself, because the sources go deep into the belly of the beast. We've been saying generator pretty loosely, but the documents clearly distinguish between the steam giants and the hydro heavyweights. Let's start with steam.
These are the speed demons of the grid.
The Siemens SST series is mentioned specifically as a case study. These things are absolute monsters, 1,900 megawatts from a single unit.
There's enough raw power to run a major metropolitan city from one single spinning shaft. And the physical conditions inside that turbine casing are hellish. Steam enters the first stage at up to 330 bar of pressure and 610 degrees Celsius.
610 Celsius. That's glowing red-hot metal.
It is visibly glowing. And it's spinning at 3,600 RPM. The centrifugal force trying to tear that solid steel apart is unimaginable. This is where we get into that concept of dendritic segregation mentioned in the metallurgy notes.
Yeah, please explain that, because when I read it, it sounded like a bone disease.
It's a defect in how massive blocks of liquid steel freeze into solid metal. When you cast a gigantic multi-ton ingot to forge a turbine rotor, the alloy elements can actually separate as it slowly cools, creating these microscopic tree-like crystal structures called dendrites. These are inherent weak points in the grain of the metal. If you have those in a rotor that is subjected to these kinds of supersonic centrifugal stresses,
They're shattered.
it violently explodes like a fragmentation bomb. So modern foundries use calcium-modified, low-alloy heat-resistant steels and incredibly complex controlled vacuum cooling processes just to make sure the internal grain structure is microscopic and perfectly uniform throughout the entire massive forging. It has to be flawless.
And the blades themselves, I saw a specific note about using titanium and something about supersonic water, which blew my mind.
Oh, this is a fascinating fluid dynamics problem. In the final low-pressure stage of the steam turbine, the steam has expanded so much that it's cooled down significantly. It's actually starting to condense back into microscopic water droplets right inside the turbine. But the blades at that final stage are massive, sometimes over 6 feet long. Because they are so long and spinning at 3,600 RPM, the tip of the blade is actually moving significantly faster than the speed of sound.
Okay, so you have suspended water droplets hanging in the casing.
And a spinning titanium blade slams into them at Mach 1.5. The relative impact velocity makes those tiny water droplets hit the metal like armor-piercing bullets. If you use normal high-grade steel, the water would literally erode the leading edge away in a matter of days. It would look like the metal had been chewed by giant rats.
So they use aerospace-grade titanium just to survive hitting water.
He brazed solid titanium shields onto the leading edges of the steel blades. Yes, it's literal armor against water droplets.
Now compare that intense speed to hydroelectric power. The hydro generators are the complete opposite end of the spectrum. They aren't fast at all.
No, they are the heavyweights. They use a vertical axis architecture, massive diameter, and they spin incredibly slowly. Depending on the waterhead, they might only spin at 75 or maybe 100 RPM.
So if they are so slow, where does the grid inertia actually come from? We just said you need pure brute physical mass. Because the equation for kinetic energy is 1/2 mass times velocity squared. If your velocity is very low, your mass has to be astronomically huge to compensate. The rotors in a place like the Three Gorges Dam in China, or the Hoover Dam, are hundreds and hundreds of tons of solid electromagnets.
There was a specific physical threat mentioned regarding hydro plants that sounded terrifying to me. The water hammer. I think we need to explain why stopping water is so dangerous, because in my normal everyday head, if I want to stop water, I just close the tap. Problem solved. Try doing that with an entire rushing river. We are talking about millions of gallons of water moving rapidly through a penstock, which is a high-pressure pipe wide enough to drive a semi-truck through. That water has mass, hundreds of thousands of tons of mass.
And it's moving fast toward the turbine.
It's rushing downhill with immense force. Now imagine the power grid suddenly disconnects due to a fault. The generator suddenly has zero electrical resistance holding it back. It immediately starts to spin out of control. Your human instinct in the control room is shut the water off right now.
Right. Slam the valve closed before it overspeeds.
If you slam that massive valve shut, that moving column of millions of gallons of water has absolutely nowhere to go. Its massive kinetic energy has to dissipate instantaneously. It creates an enormous high-pressure shock wave that travels back up the pipe, a water hammer.
And on this industrial scale...
On this scale, it's like a bomb going off inside the concrete plumbing of the dam. It will instantly rupture high-tensile steel. It can literally blow the penstock apart from the inside and catastrophically flood the entire power station. You cannot stop it fast. You have to close the wicket gates very, very slowly, over 10, maybe 20 seconds.
But wait, during those 20 seconds, the turbine is still getting pushed by the water. It's going to overspeed and tear itself apart.
That is exactly why hydro rotors are built so incredibly heavy. They act as mechanical sponges. They are physically designed to soak up all that excess kinetic energy spinning faster and faster, maybe safely reaching 140% of their rated speed without flying apart. Their mass buys the mechanical valves the time they need to close gently.
So the immense inertia of a dam isn't just to keep the grid frequency stable, it's actually designed to save the dam itself from exploding.
It's pure self-preservation. Grid stability is almost a happy byproduct.
I really loved the specific detail about the auxiliary systems in the notes. Specifically, this crazy idea that these machines are so incredibly heavy they can't even sit perfectly still without destroying themselves.
Oh, the jacking oil system.
Yeah.
This is a critical piece of extreme engineering.
Please explain this, because jacking oil sounds like you're changing a tire on a car.
It's a similar concept, but with fluid dynamics instead of a mechanical jack. Imagine a 500-ton steel shaft resting inside a stationary metal bearing. Gravity is pulling that shaft down with such immense force that it physically squeezes every single molecule of lubricating oil out of the microscopic gap at the bottom. The steel is in direct physical contact with the bearing metal.
So if you tried to turn the machine on from a dead stop?
The static friction would act like an absolute brake. You would grind the ultra-smooth bearing surface into metal shavings in seconds. You would destroy a multi-million-dollar machine before it even completed a single revolution.
So what do the operators do?
Before they even think about hitting the start button, they engage high-pressure auxiliary pumps, pushing oil at around 6.9 megapascals. They inject this extreme pressure oil directly into the tiny gap under the resting shaft.
To lift it?
To physically lift 500 tons of solid steel using nothing but liquid pressure. Just a tiny amount, a few hundredths of a millimeter. But it's enough so that the massive shaft is literally floating on a microscopic film of oil. True levitation. Only then is it safe to introduce steam and start turning.
That is wild. And then there's the cooling system.
Yeah.
We're cooling these giant electrical machines with hydrogen gas. That seems completely counterintuitive to me. Hydrogen is famously explosive.
It's extremely explosive. The Hindenburg disaster proved that quite clearly. But power plant engineers absolutely love hydrogen for two very specific physical properties. One, it conducts heat away from the copper windings about 7 times better than regular air. 2, it is incredibly light.
Light? Why does the weight of the cooling gas matter inside a closed box?
Low density. When you are spinning a massive uneven rotor at 3,600 RPM, the air resistance, what engineers call windage friction, is a huge mechanical drag. It physically wastes megawatts of power just churning the air inside the casing. Hydrogen gas is slippery. It's 1/14 the density of air. It reduces that aerodynamic drag so much that you actually get about 25% more electrical power out of the exact same physical generator just by swapping the internal air for hydrogen.
But the risk factor?
The risk is very real. A mixture of anywhere between 6% and 71% hydrogen in normal air is highly combustible.
So if there's a tiny leak in the casing?
If air gets in or hydrogen gets out near a spark boom, that's why the outer generator casings are built as blast-proof pressure vessels. They use complex vacuum-treated oil-sealed clans around the spinning shaft just to prevent leaks. And they rigorously monitor the internal gas to keep the purity at 90% or higher. As long as it's pure hydrogen with no oxygen present, it physically cannot burn.
So it's literally living dangerously for the sake of thermodynamic efficiency.
It is a highly calculated risk that the industry has accepted.
Let's move to section 6 of the outline. Startup and synchronization. Because I think most people have this Hollywood movie-style idea that you just walk into a control room, hit a big green button on a console, and the power plant roars to life, and the city lights up.
I wish. It is the exact opposite of a movie scene. It is incredibly slow, tedious, and highly stressful for the operators.
Yeah.
Especially for a massive steam turbine.
The notes detail the cold start process.
Right. If a steam turbine has been offline for more than 40 hours, the internal metal has cooled down to room temperature. If you suddenly blast 600-degree superheated steam into a cold steel machine, what happens to the metal?
It expands.
Rapidly.
Yeah.
And unevenly. The spinning rotor has less mass than the thick stationary casing, so the rotor heats up and expands much faster. It physically grows lengthwise. If you heat it up too fast, the rotor will actually grow longer than the casing, and the spinning blades will crash violently into the stationary diaphragms.
So you have to sort of bake it in the oven slowly?
You have to soak it. The operators put it on a turning gear, spinning it very slowly, while emitting just a tiny whisper of warm steam for over an hour. You are nursing the internal temperature up degree by painstaking degree, constantly watching the differential expansion monitors. It's a very delicate thermal dance.
And once it's finally hot and spinning at full speed, you have the wedding. Synchronization.
This is the ultimate moment of truth in power generation. You have a 500-ton machine spinning at exactly 3,600 RPM in your plant, and you want to connect it to the continental grid, which is also spinning at exactly 3,600 RPM.
You essentially have to merge onto a highway.
But the highway traffic is a solid brick wall if you miss your gap. You have to match 4 electrical parameters perfectly before you close the massive breaker: voltage, magnitude, frequency, phase angle, and phase sequence.
I really want to know what happens if you get it wrong. What if an operator is tired on a night shift and closes the breaker when the phase angle is just a few degrees off?
It's called out-of-phase synchronization, and it is one of the most catastrophic operator errors possible.
How catastrophic are we talking?
Remember that magnetic grip we talked about?
Mm-hmm.
If you connect the generator when the alternating current waves are out of sync, the immense power of the entire continental grid instantly rushes in and tries to force your massive generator into lockstep in a fraction of a second. It applies a sudden mechanical torque spike to the shaft that can be up to 20 times the normal operating maximum.
Just instantaneously.
In milliseconds.
Yeah.
It is enough shear force to snap a solid steel shaft the size of a tree trunk, like a dry twig.
Yeah.
It can physically twist the heavy copper rotor windings into a pretzel. I've seen photos and failure reports of generator shafts that look like wrung-out wet towels. It completely destroys the machine and highly likely causes a massive catastrophic explosion in the step-up transformer yard outside.
So the operator's just staring at that synchronization dial on the board.
Just sweating, waiting for the physical needle to hit exactly 12 o'clock before hitting the button. It's the most stressful action in the industry.
This actually brings us to the true crime section of the deep dive. When the physics fail, we've built this incredible continental machine, but as we've seen, it has severe physical limits.
It is fragile.
Yeah.
And the specific way it fails tells us a lot about the future of energy.
We need to talk about RTF.
Right? The rate of change of frequency.
Why is this the single metric that all grid operators are terrified of?
Because it is essentially the measure of grid panic. If a large power plant suddenly trips offline, the grid frequency inevitably drops. That's a normal daily occurrence. But the vital question is, how fast does it drop? Does it glide down gently over 10 seconds, giving everyone time to react? Or does it plummet off a cliff in 1 second?
And inertia is the parachute here.
Exactly. High physical inertia means a slow drop, a gentle glide. Low inertia, which we're seeing a lot more of lately, means a terrifying nosedive. If the RTF hits 1 hertz per second, you are officially in the red zone.
Why is 1 hertz per second the magic line for disaster?
Because the automated digital safety systems, the protection relays, need processing time to think. They need maybe 100 to 250 milliseconds to measure the drop, verify it isn't a glitch, and send a trip signal to open breakers. If the frequency falls faster than the computer can run its logic loop, the grid physically collapses before the safety systems can deploy the lifeboats.
Let's look at the South Australia blackout in 2016. The sources highlight this as the classic modern case study of low inertia collapse.
The industry calls this the black system event. It changed how everyone looks at renewables.
Set the scene for us. It's September 2016.
It's completely apocalyptic weather. A massive, once-in-50-years storm system hits the state. Tornadoes are physically touching down. Meteorologists recorded something like 80,000 lightning strikes in a few hours.
80,000. So the physical transmission wires are taking an absolute beating.
Massive high-voltage transmission towers are crumpling like paper. As these main lines hit the ground, the voltage across the state grid violently spikes and dips. Now, South Australia has a very high penetration of wind farms.
And wind farms are largely power electronics, not heavy spinning steel synchronized to the grid.
Correct, they use inverters. When the grid voltage dipped wildly, the self-protection software on dozens of wind turbines looked at the dirty power and said, this is unsafe for our hardware, and automatically disconnected them from the grid.
So suddenly, right in the middle of a storm, you lose a massive chunk of your local generation.
Around 450 megawatts just vanished in seconds.
Yeah.
So the South Australian grid desperately tries to pull that replacement power from the neighboring state Victoria through a massive tie line called the Haywood Interconnector.
The interstate extension cord.
But the sudden power surge rushing across that line was too massive. The interconnector's own safety relays saw the overload and tripped the line open to save it from melting.
Snap. So South Australia is suddenly an electrical island.
An island with a massive power deficit and, crucially, critically low physical inertia because the wind farms were gone and they don't provide synchronous spinning inertia anyway.
So the ROTLF
Was absolutely extreme.
Yeah.
The frequency plummeted to 47 hertz in barely a second. The automated under-frequency load shedding system, which is designed to deliberately black out certain neighborhoods to save the main grid, triggered, but the relays were just too slow. The grid crashed faster than the physical mechanical switches could open.
The entire state went completely dark.
850,000 customers lost power. Heavy industry, hospitals, everything. All because the drop in the heartbeat was simply faster than the digital reflex.
Now, I want to compare that nightmare scenario to the UK blackout in 2019. This one is really fascinating to me because it wasn't a massive continental storm. It was literally just one lightning strike.
One single routine lightning strike near Cambridge on a normal Friday afternoon. And the irony is the local protection systems actually worked perfectly. They cleared the electrical fault from the lightning in 0.1 seconds.
So what actually went wrong to cause a national event?
Confusion in the automated systems. The Hornsea offshore wind farm and the Little Barford gas turbine station both saw the tiny voltage interference from the lightning strike and got confused by the signal. Their internal software tripped them offline unexpectedly.
So you unexpectedly lose significant power generation. The frequency drops.
It dropped to 48.8 hertz. The national safety systems kicked in exactly as designed and automatically cut power to about 1 million people across the country. It worked. The grid stabilized. The cascade was stopped.
So it was technically a success.
From the perspective of the grid control room, yes. But this is where the law of unintended consequences rears its head. The grid frequency dropped to 48.8 hertz. The power stayed on for most of the country. We should have been fine. But the commuters on the Thameslink railway network were definitely not fine.
The commuter trains.
Yes. The new Class 700 trains. They're essentially highly sophisticated rolling computers, and they have extremely sensitive onboard protection systems designed to protect the train's sensitive traction motors from bad grid power.
I see exactly where this is going.
The train's computer saw the national grid frequency dip to 48.8 hertz. It looked at that signal and said, this power is out of spec, it's dangerous. So the train did exactly what its programmers told it to do. It safely disconnected itself from the overhead line to save its electronics.
It bricked itself on the tracks.
Instantly.
Yeah.
60 separate trains, fully loaded with Friday afternoon commuters, simultaneously went completely dead across the network. And here is the absolute kicker to reboot the safety software on a Class 700 train.
Don't tell me you just have to turn it off and on again.
You do, but the technician actually has to physically walk to a specific panel at the rear of the train to access the hard reset switch.
And these are incredibly long commuter trains packed with people.
So you have tens of thousands of people trapped in dark, unair-conditioned metal tubes, blocking the entire rail network, waiting for a driver to squeeze through crowds and walk 200 meters, all because one lightning strike in Cambridge confused a computer algorithm in London.
That is just the ultimate modern irony. The massive physical grid was saved, but the highly advanced society it serves was totally paralyzed because the endpoint machines were simply too sensitive.
Exactly. It shows that as we digitize everything and tighten our tolerances for efficiency, we introduce these totally new, highly fragile, complex interactions.
Let's hit one last case study before we wrap up. Continental Europe 2021, the day the European grid literally split in half.
This was an incredibly close call for the continent. A specific transmission substation failed in Croatia, and the resulting cascade effect literally severed the physical connection between the northwest of Europe and the southeast of Europe.
So you essentially have two massive separate islands floating in the dark.
Yes. The Northwest Islands suddenly had slightly less power generation than it needed, so its frequency began dropping. The Southeast Island suddenly had too much generation trapped inside it, so its frequency began to dangerously spike.
But the lights generally stayed on across Europe.
They did. And why? Because the synchronized European grid is unimaginably massive. It has huge amounts of physical inertia from all the heavy coal and nuclear plants spinning in places like France and Germany. That heavy spinning mass made the Aro Kofi very, very slow.
It glided down.
It glided beautifully. That slow, gentle drop gave the massive industrial consumers in France and Italy plenty of time to automatically detect the issue and safely disconnect their factories to balance the load. It gave the mechanical plant governors time to smoothly open valves. The raw inertia bought the grid operators a full 5 minutes to react and stabilize the two islands before they collapsed.
So the sheer mass of the steel saved Europe from a catastrophic continent-wide blackout.
It was the ultimate shock absorber. It absorbed a continental fracture with barely a flicker for most people.
We have covered so much ground today. From the basic physics of Isaac Newton to the metallurgy of titanium turbine blades to the digital chaos of modern blackouts. And I have to say, I am personally never going to look at a high-voltage power line the same way again.
It really does change your perspective, doesn't
Yeah.
it? When you realize it's the most complex, synchronized machine ever built by humanity.
But if there's one overarching takeaway from all these documents, it's that this massive system is actively changing right under our feet. We've built all this incredible stability entirely on the back of heavy spinning steel.
And we are rapidly removing that steel from the equation. As we shut down massive coal and nuclear plants for environmental reasons and move to wind and solar power, we are systematically taking the heavy flywheels off the bicycle. We are transitioning to inverter-based resources, which provide precisely zero physical spinning inertia.
That seems like a massive unresolved problem.
It is arguably the defining engineering challenge of the next 20 years. How do you replace the physical heartbeat of steel? Engineers are experimenting right now with things like synthetic inertia, using giant batteries and incredibly fast software to mimic the physics of a spinning turbine. But it's a fundamental paradigm shift in how the machine actually operates. We are actively replacing physical momentum with digital algorithms.
Which, as we saw with the UK train disaster, carries its own set of deeply unpredictable, cascading risks.
Precisely. We are trading mechanical robustness for digital efficiency.
I really want to leave the listener with a final thought today, something to just chew on later. We started this whole deep dive by talking about the humble light switch on your wall.
The human interface to the machine.
The next time you walk into a dark room this evening and you reach your hand out for that switch, just stop for a second. Don't just flip it mindlessly.
Think about what you are actually physically doing.
You aren't just sending a tiny digital signal to a smart meter. You are reaching out invisibly across hundreds of miles of copper wire, and you are physically grabbing a 500-ton steel shaft that is spinning in an absolute hellscape of high-pressure steam and heat. You are applying a magnetic brake. You are slowing that massive steel down. You are an active physical part of the machine.
And for that split second, before the coal burns or the gas ignites, civilization is running on absolutely nothing but the coasting momentum of that steel. It really is a miracle when you think about it. I was reading through these notes, and the term superorganism came up repeatedly.
Oh, yeah, a lot.
The idea that the grid isn't just a machine, but it's like a living, breathing thing.
It's a very powerful metaphor. And as we'll see later, it's not just poetry either. It's actual thermodynamics. The grid behaves like a biological entity.
But before we get to the biology comparisons, we have to understand the stakes here. Why change the physics at all?
Right. Why not just keep doing what we've been doing for 100 years?
Exactly. If it ain't broke, don't fix it.
Well, this brings us to the global imperative. This is the aggressive push for decarbonization. We are moving toward wind and solar at an absolute breakneck pace.
Correct. And let's be clear up front, the sources highlight that this is essential. This isn't a debate about climate change.
No, not at all.
This is about the strict engineering reality of a clean energy future.
Right. But here is where it gets absolutely fascinating. The problem isn't the energy source itself. It's not that wind or solar are somehow bad energy. An electron is an electron.
Your toaster doesn't care if the electron came from a solar panel or a lump of coal.
Exactly. But the grid cares.
The grid cares a lot.
It does. The problem is the physics of how that energy actually enters the system. We are replacing the delivery mechanism itself, and that changes literally everything.
So this is the core tension. We want the green energy.
Yeah.
We need it.
Yeah.
But the green energy doesn't behave like the old energy. So let's unpack this, what they call the inertia crisis.
Ah.
Because that's the technical term that just kept popping up everywhere in the reading.
It did. The grid is losing its inertia.
That is the term. To understand why that actually matters, we have to look at the old guard.
Right, the traditional stuff.
For the last century, practically all of our electricity came from the exact same basic mechanical process. Whether you were burning coal, burning natural gas, using nuclear fission to boil water.
Or even holding back a river for hydropower.
The fuel was different, but the machine was essentially the same.
Precisely. The end result was always using that energy to spin a turbine. And when we say turbine, I really don't want you to picture a little desk fan.
Oh no, these things are absolute monsters.
We are talking about rotors that weigh anywhere from 50 to 200 tons. Solid steel and copper.
200 tons.
And they are spinning at incredibly high speeds, usually 3,000 or 3,600 revolutions per minute, depending on where you are in the world.
Okay, let's just pause on that image for a second. A 200-ton piece of solid metal spinning at 3,600 RPM. The amount of kinetic energy stored in that moving mass it's hard to even comprehend.
It's immense. Think of it like a freight train. A very heavy, very long freight train moving at full speed. It has massive momentum.
Like a heavy flywheel. Once it's going, it really, really does not want to stop.
Precisely. That resistance to change, that stubbornness of the physical object is called inertia. And for the entire history of the electrical grid, this inertia was basically a free gift.
Just a byproduct.
Right. It was a natural, abundant byproduct of how we generated power. We didn't have to go out and build special inertia machines. It was just there because the generators were incredibly heavy.
So this is the kinetic buffer the sources talk about. It's like
Right.
a giant shock absorber.
Yes. Imagine a scenario where a large power plant suddenly fails. Maybe a lightning strike takes out a transmission line or a generator trips offline unexpectedly.
So instantly, there is a deficit of power.
Exactly. The demand is suddenly higher than the supply. And the frequency of the grid, that heartbeat of 60 hertz, it starts to plummet.
Because the load is dragging it down.
Right. But because you have these thousands of massive turbines spinning across the entire continent, they don't just stop instantly.
Physics forbids it.
Exactly. They literally feel the drag of the failing grid. The electromagnetic forces inside the generator pull on them, trying to slow them down.
And because they are so insanely heavy, they fight back.
They refuse to slow down immediately. They literally release their stored kinetic energy back into the wires. They essentially say, I am going to keep spinning and I am going to push this power out just a little bit longer.
It's like if you're riding a really heavy bike super fast and you stop pedaling, you keep coasting. You don't just stop dead the moment your legs stop moving.
That coasting is exactly what saves the grid in those first few critical seconds.
Oh.
It arrests the decline. It buys precious time for the control systems to wake up and react.
It smooths out all the chaos.
Right. But now, enter the new challenger.
Inverter-based resources. Solar and wind.
Let's look at solar panels first. They are entirely static. They have zero moving parts. There is no turbine, no spinning mass, no heavy iron.
Just flat glass.
Right. They harvest sunlight and create electricity through a chemical reaction, but they store absolutely zero kinetic energy.
So if a cloud goes over, or the grid trips, a solar panel provides no coasting.
None at all. It's instantaneous. If the sun goes away, or if the grid demands a sudden surge, the solar panel has nothing in the tank to give. It's just on or it's off.
Now, wind turbines are a bit trickier, right? Because I drive past wind farms and those blades are massive. They're spinning. I'd look at that and think, hey, that's inertia. That's a giant spinning thing.
You would definitely think so. And physically, yes, there is rotating mass there. But unlike a coal turbine, the rotation of a modern wind turbine is physically and electrically decoupled from the grid frequency.
Decoupled? That sounds like a bad relationship status.
It kind of is. They aren't in a committed relationship with the grid frequency. A coal turbine is locked in step. If the grid slows down, the turbine physically slows down. They are married.
So what is the wind turbine doing?
A wind turbine is spinning at whatever speed the wind dictates, which might not match the grid's 60 hertz at all.
So the grid literally can't feel their weight.
Essentially, yes.
Yeah.
And this is because of the device that sits right between the renewable source and the grid itself, the inverter.
The magic box.
It really is a magic box. Solar panels produce direct current, DC. The grid runs on alternating current, AC. Wind turbines produce what the sources call wild AC.
Wild AC.
Yeah, it's variable, it's messy, the frequency is just all over the place. The grid needs perfectly synchronized, totally clean 60 hertz AC.
So the inverter takes those messy raw ingredients, the DC or the wild AC, and basically cooks it into a perfect souffle.
That's a fantastic analogy.
Okay.
It uses advanced power electronics, these silicon switches turning on and off thousands of times a second to synthesize a perfect sine wave.
So it's a digital recreation of power.
Right. But because it's doing this electronically, purely buffered by silicon, it provides no natural physical inertia.
It's just a simulation.
It acts like a generator, sure, but it lacks the physical body of a generator. If the grid frequency drops, a standard inverter just doesn't care, doesn't feel the drag. It doesn't instinctively push back with kinetic energy.
It just keeps doing what its code tells it to do until it can't anymore.
Exactly. So as we shut down the big heavy coal and gas plants, the heavy metal, and replace them with solar and wind, the total rotating mass of the grid shrinks.
We are quite literally losing weight.
We are. It erodes the kinetic buffer. The grid becomes lighter in a very real physics sense. It becomes twitchy, volatile.
And in the sources mentioned this leads to a weak system. That sounds like a very specific engineering term, not just a casual insult.
Oh, it is deeply technical. It's not just about the frequency dropping fast, it's about short-circuit power.
Brute force. That was the phrase that really stood out to me in the notes. The grid needs brute force.
It absolutely does. Think about what happens when a tree falls on a power line during a major storm, or a lightning bolt strikes a substation. That creates a short circuit. The electricity suddenly wants to rush directly into the ground. It's a massive fault.
And we need to clear that fault instantly to prevent fires or massive equipment damage.
Right. To clear the fault, you need to blow a fuse or trip a heavy circuit breaker. But here is the massive paradox. To blow a large industrial fuse, you need a massive surge of current. You need a huge spike of power.
You essentially need to punch the fuse to make it pop.
Exactly. Traditional generators, because they are big coils of copper and iron with all that spinning momentum, can deliver a massive punch of current like 5 or 6 times their normal output for a split second.
Wow.
They have the actual brute force to blow the fuse and isolate the problem instantly.
And inverters.
Inverters are delicate. They are made of silicon switches, IGBTs, or MOSFETs. These chips have very strict thermal limits.
They're basically like computer processors.
Exactly. If you try to push a brute force current through them, they will fry in milliseconds. They will literally melt.
So they're programmed to protect themselves first.
Exactly. They clamp the current down. They absolutely refuse to provide that surge.
Which means the fuse doesn't blow.
It might not. Or the protective relays, the sensors that watch for these faults, might just get confused. They are looking for a big spike and they don't see it.
So the fault persists.
Yes. This leads to deeper voltage dips. The zone of destruction or influence during a fault gets much wider.
We've actually seen this happen, right?
Yeah.
The notes specifically mentioned the 2016 blackout in South Australia and incidents in the UK.
We have cascading failures. When you lose that physical inertia and that short-circuit strength, things happen way too fast for the old systems to catch. The grid becomes fragile.
It's like replacing a steel suspension bridge with a spider web.
That's a great way to put it. It might look the same, it might span the exact same gap, but it reacts very, very differently when the wind blows.
So we're taking away the physical safety net, the inertia, and we have to replace it with something else entirely. Control. We need smarter, faster control.
Right.
But to understand where we're going with control, the source material suggests we really need to look back at where we came from. We need to do a little bit of time travel.
We do. We need to go back to the 1920s and 30s, the era of the manual dispatcher.
I love this section of the research. It feels like a black and white noir film. The notes describe the Los Angeles Bureau of Power and Light.
It really does set a scene. Before we had microprocessors, before we had SCADA systems or even solid-state electronics, the stability of the grid rested entirely on human perception.
The load dispatcher. The notes describe their office as the absolute nerve center.
Imagine a massive room with high ceilings, probably filled with cigar smoke. The walls are covered in massive control boards, not screens, but physical boards with painted diagrams of the transmission lines.
And little light bulbs showing what's open and what's closed.
Exactly. It resembled the traffic maps of a railroad system.
And the people working in this room?
These operators were working 24 hours a day, and their sole job was to manually balance the supply and demand of electricity for an entire major city. If Los Angeles turned on its lights, these guys had to physically find the power.
And we have a specific name here in the documents. P.J. Vogel. The chief dispatcher.
PJ Vogel. He perfectly represents the human algorithm. Think about what his job actually entailed. He didn't have a computer algorithm telling him what to optimize. He had to manually monitor water flows in the aqueducts coming from the Owens Valley.
He had to calculate reservoir elevations
Right.
with a slide rule to know how much power the hydro plants could generate that day.
Yes. And the actual control, this is the part that just blows my mind, the regulating unit. How did they actually keep the frequency at 60 Hz?
It was incredibly analog, right?
Pure analog. They would designate one specific power plant as the regulator. The operators in that powerhouse would literally stand there and stare at a physical frequency dial, a mechanical needle on a gauge,
Just watching a needle twitch.
all day long.
All day. And if that needle dipped to the left, indicating that the frequency was dropping, maybe people were waking up and making coffee, the operator would physically grab a massive valve wheel or a lever and turn it.
Manual feedback.
Literally shouting, "More steam, more water." They were manually injecting energy to fight the needle. They were the servo motor. But the lag there, the human latency.
It was massive. Think about the control loop. The needle moves. The eye sees it. The brain processes it. The muscles turn the valve. Then the actual physics of the water hitting the turbine takes time.
And if the central dispatcher, PJ Vogel, needed to change the overall plan, he had to pick up a literal telephone.
Hello, Powerhouse 4, we need more juice.
Exactly.
Or they used early radios like the SCR 536 walkie-talkie mentioned in the notes. It introduced noise, static, and delay. It was a very high latency control loop. It was like playing the telephone game, but if you got the message wrong, the entire city went dark.
The notes also mentioned the Pennsylvania Railroad. They actually had their own grid.
They did. In the 1920s, the national grid as we know it didn't exist at all. It was a patchwork of isolated islands. The Pennsylvania Railroad built a dedicated 25 hertz grid just for their traction motors.
And they had their own power director centers.
Yes. It shows how fragmented the world was back then. Everyone was their own island.
But islands are inefficient. If your single generator breaks, your lights go out. So logically, they started connecting the islands together.
Right, the interconnection paradox.
Exactly. As cities grew, they realized that connecting their grids together was mutually beneficial. If I lose a generator, I can borrow power from you. It shares the risk.
It smooths out the bumps, safety in numbers.
But as you interconnect, the complexity simply explodes.
It does. Suddenly you aren't just watching one city, you're watching an entire region. The physical flows of power become way too complex for a human brain to calculate in real time.
The reaction times required became too fast. We literally hit the physical limit of the human operator. PJ Vogel just couldn't keep up anymore.
We needed a machine to watch the machine.
We needed automation. And this leads us to the modern hierarchy of defense. This is how the grid protects itself today.
Okay, let's unpack this hierarchy because the sources are very clear on this. Grid defense happens in strict stages. It's not just one big thing, it's a timeline.
It's a temporal sequence. It starts incredibly fast and gets slower. And it starts with primary control.
The mechanical reflex.
Think of this as the knee-jerk reaction. If the doctor taps your knee with that little rubber hammer, your leg naturally kicks. You don't think about it. Your brain isn't even involved. It happens purely at the level of the nerve and muscle.
Primary control is the grid's knee-jerk reflex. It happens within seconds.
And the device responsible for this is the governor.
The governor. Every single turbine has one. And the history of this device is a brilliant lesson in classical physics. The flyball mechanism.
I've seen pictures of these in old steam engine diagrams. The two metal spheres spinning around on a shaft.
Yes, it's pure genius in its simplicity. Picture a vertical shaft spinning in exact sync with the main turbine. Attached to it are two hinged arms with heavy metal balls on the ends. As the turbine speeds up, centrifugal force throws those balls outward.
Like when you spin around with your arms out, you feel the pull pulling your hands away.
Exactly, and through a direct mechanical linkage, as those balls move outward, they physically push a lever that closes the steam valve.
So if it spins too fast, the balls fly out, the valve closes, and it naturally slows down.
And if it slows down, gravity pulls the balls back in, the valve opens, and it speeds back up. It's a perfect negative feedback loop. Speed goes up, balls go out, valve closes, speed comes down.
It's purely mechanical. No computer, no electricity even, just physics regulating physics.
That's the historical version. But today, obviously, we're a bit more high-tech.
Today we use the digital reflex. electrohydraulic governors.
Right. We have active proximity probes that measure the shaft speed with microscopic precision. They feed that data directly into a microprocessor, like the Rockwell automation systems explicitly mentioned in the notes.
But you still need to actually move a massive valve. A computer chip can't push a solid steel valve against super high pressure steam.
No, it can't. That's why we need the muscle, the hydraulic amplifier. The computer sends tiny low-voltage electronic signal. That signal opens a small pilot valve, which then releases a massive surge of hydraulic fluid oil under immense pressure.
So the electrical signal triggers the hydraulic fluid, and the fluid pushes the heavy piston.
It pushes a servo motor that physically fights the crushing turbulent pressure of the steam or water. We are talking about forces that would easily crush a car, perfectly controlled by a microchip, and this all happens in milliseconds.
Now, there's a concept here that I found really tricky when I was reading, but the sources say it's crucial to understanding how these massive generators play nice together. Droop control.
Ah, yes, speed droop. It sounds like a bad thing. Degradation of sensitivity.
Right. Why would we intentionally degrade our own control system? Why don't we want it to be perfectly sensitive?
Imagine you have two people trying to carry a very heavy sofa up a flight of stairs. If both of them are trying to perfectly control the height to the exact millimeter, rigidly locking their arms, they will just fight each other constantly.
One lifts a tiny bit, the other feels the weight shift and drops, then the first one lifts even more. It becomes totally chaotic. They oscillate.
Exactly. A feedback loop. They're basically fighting for total control.
So to prevent generators from fighting each other, we program them to be a little bit soft.
We tell them, if the overall load increases, don't try to hold the speed perfectly at 60. Let it drop just a little bit.
So everyone agrees to let the standards slip just a tiny bit so that they can actually work together smoothly.
In a way, yes. It distributes the load evenly across all the machines. The end result is that primary control arrests the fall. It stops the bleeding. But it leaves the grid stabilized at a slightly off nominal value.
Like maybe 59.9 hertz instead of a perfect 60?
Exactly. It catches the falling knife, but it doesn't put it back in the drawer.
That is a perfect analogy. Primary control catches the knife. But now the knife is just hovering there at 59.9 hertz. Clocks will start to run slow. Industrial machines will run inefficiently. To put it back in the drawer, to get back to perfect 60.000 hertz, we need the brain. We need secondary control.
And this is where the math really comes in. Automatic Generation Control, or AGC.
AGC. This operates on a timescale of minutes, not seconds.
Right. While primary control is totally decentralized, every plant reacting on its own reflex. Secondary control is centralized within a specific region. It's the conductor of the entire orchestra.
And the metric they use, this seems to be the absolute holy grail of grid operators. The ACE, area control error.
The ACE is the foundational metric of modern grid stability. To really understand it, you have to realize the grid isn't just one big amorphous blob of wires. It's strictly divided into balancing authorities.
Like states or provinces.
Sometimes, or just specific utility territories. Each authority has a virtual fence around it, and they are fiercely responsible for their own internal balance.
The ACE calculation basically asks two questions. Are you importing or exporting what you promised? And two, are you helping the overall frequency?
Exactly. So if my ACE is exactly 0,
you are a perfect citizen. You are generating exactly enough for your own people, plus whatever you explicitly sold to your neighbors. You are in perfect equilibrium.
And if my ACE is negative?
You are a bad roommate. You are leaning on your neighbors. You aren't generating enough to cover your own local load, so you are physically sucking power in from the surrounding grid just to keep your lights on. You are dragging the entire system down.
And a positive ACE?
You're over-generating, pushing uncontracted power out, which sounds like it would be a good thing, but it pushes the frequency up, which is also extremely dangerous.
Right. So the core goal of the brain, the AGC computer, is to drive that number to 0.
Constantly. Every few seconds, the energy management system, which is a massive supercomputer system, calculates the ACE. Then it sends digital rave or lower signals directly to the power plants.
Turbine 4, give me 5 more megawatts.
Exactly, and it does this entirely automatically. No PJ Vogel turning a valve by hand. The computer talks to the digital governor talks to the hydraulics move the massive physical valve.
It's a beautiful system when it works. Each region acts entirely selfishly. I want my ACE to be 0.
And by each region selfishly cleaning up its own mess, the entire continent inadvertently stays in perfect balance. It's the sheer beauty of decentralized optimization.
It's Adam Smith's invisible hand, but literally for electrons.
Which brings us to the biggest picture of all, the continental superorganism.
This is where we leave the pure mechanics and enter the realm of almost biological philosophy.
The sources genuinely compare the grid to a living cell. It seems like a massive stretch until you actually read the details.
They do. In advanced biology, we talk about dissipative systems, structures that naturally maintain their internal order by consuming massive amounts of external energy.
A cell uses electrical fields, transepithelial fields, to detect a physical wound and heal it. If you cut your skin, the electrical potential changes instantly, signaling nearby cells to migrate and heal the breach.
And the grid uses frequency exactly the same way.
Frequency is the nervous system.
Exactly. If the frequency dips, the grid physically feels the wound, it feels the sudden imbalance. And through primary and secondary control, it immediately orchestrates a massive healing response.
The sources actually state, a cell dies without electrical dimension, a grid collapses without synchronization.
The scale of this organism is just hard to wrap your head around. The European Synchronous Area, ENSO.
It's staggering. We are talking about 400 million customers, from the sunny coast of Portugal all the way deep into Eastern Europe.
Every single generator, every huge motor in every factory, every washing machine, every fan is physically locked to the exact same 50.0000 hertz rhythm.
It's a literal collective heartbeat.
It is. They are magnetically coupled together. If a generator in Spain speeds up, a generator in Poland instantly feels it. They are part of the exact same body.
And sheer size matters here. The bigger the organism, the more stable it naturally is.
Notice that physical inertia we talked about earlier.
The invisible shock absorber.
Right. If you have 1,000 massive generators spinning and one suddenly fails, the other 999 barely even feel it. The shock is heavily diluted across the massive collective pool of inertia.
And this leads to some absolutely fascinating geopolitics. Countries desperately want to join the organism. It's not just about selling extra power, it's about raw stability. Being part of the big club simply makes you safer.
It is fundamentally an engineering desire, but it has massive political implications. Just look at Turkey.
The notes say this was a 10-year engineering mission.
A full decade of engineering. Turkey wanted to synchronize with Europe, but you can't just plug a country in like a toaster. If their internal grid is unstable, they will drag all of Europe down with them.
They had to heavily upgrade all their governors, install advanced protection relays everywhere. They had to mathematically prove they wouldn't be a bad roommate.
And the physical anchor for this incredible connection is the Ataturk Dam in southeastern Turkey.
It's a beast. 8 massive Francis turbines, 300 megawatts each.
That's 2,400 megawatts of sheer rotating mass.
When Turkey finally synchronized with Europe, that dam essentially became the eastern anchor of the entire European grid. It added that massive physical inertia to the collective pool.
So, hypothetically, a wind gust in Portugal.
A drop in wind power in northern Germany causes a microscopic frequency dip. Before a human operator in Berlin can even blink, the mechanical governors on the Ataturk Dam in Turkey detect that dip.
Via the frequency drop.
Right, and they automatically open their valves slightly. Power flows completely invisibly across borders, without passports, without customs agents.
Physics really doesn't care about human sovereignty. The grid heals the wound using physical resources from thousands of miles away automatically.
Speaking of sovereignty, we absolutely have to talk about the Baltic states. Estonia, Latvia, Lithuania. This is happening, well, depending on exactly when you listen to this, it might have just happened. February 2025.
February 9th, 2025, exactly at 14.05 Eastern European Time. This is a genuinely historic moment in grid physics.
They're permanently disconnecting from the Russian grid.
Yes. For decades, dating all the way back to the Soviet era, the Baltic states completely relied on the Russian and Belarusian systems for their primary frequency control. Their entire heartbeat was managed from Moscow.
That's a highly precarious position to be in, especially given the current state of the world.
Extremely precarious. It meant their very energy security was deeply tethered to a foreign power. If Russia wanted to, they could easily destabilize the Baltic grids.
So they have executed this massive, years-long infrastructure project to physically cut those ties.
Literally opening the physical high-voltage switches.
And synchronize themselves directly with continental Europe via Poland.
They are quite literally transplanting themselves from one superorganism to another.
It's a perfect analogy. And it requires immense underlying trust. They are fully trusting the decentralized algorithms of the area control era managed by their European partners.
They are quite literally betting their national security on the raw physics of the European grid.
It really highlights that frequency isn't just a dry technical spec on a datasheet. It's a bond. It's a geopolitical treaty written in hertz.
Absolutely. It is the ultimate expression of trust between sovereign nations. You are sharing your heartbeat.
So trying to bring this all back home, to start out just looking at the outlet on the wall.
Right.
We've gone from spinning heavy iron to microscopic silicon chips, from P.J. Vogel nervously staring at a twitching needle to continent-spanning superorganisms and intense geopolitical maneuvering.
It's been quite a journey.
It has, but we have to circle back to the inertia crisis itself. We are building this massive, beautifully complex superorganism, but we are simultaneously completely removing its bones. We're taking out the heavy metal and putting in lightweight silicon.
That is the ultimate paradox here. We are moving from the mechanical reflex, which is robust, highly physical, and totally undeniable, to a purely digital reflex.
Can the software really replace the physics? Because at the end of the day, that's exactly what we're asking it to do.
That is the multi-billion-dollar engineering question. We are asking lines of code and algorithms to do exactly what a massive spinning rock does naturally. We are genuinely trying to code momentum.
It's like trying to program a feather to act exactly like a bowling ball.
And we are getting better at it, slowly. There are highly advanced technologies called grid-forming inverters that try to mimic this inertia synthetically.
How do they do that?
They try to digitally emulate the precise math of the spinning rock using ultra-fast current injection. But they are still ultimately silicon. They still have rigid thermal limits. They simply can't take a massive physical punch like a huge chunk of iron can.
So the paradigm shift the source has mentioned, it's not just about installing a bunch of solar panels in a field.
No.
It's about completely, fundamentally rethinking how we control the entire machine.
We have to engineer a digital nervous system that is vastly faster than ever before, because without the physical inertia to slow things down, the grid is going to move much faster.
Accidents will happen faster.
Collapses could happen faster. Our control systems must be faster than the underlying chaos.
It's basically a race between our ability to code complex algorithms and the actual speed of light.
In a very real way, yes. And we don't honestly know for sure if we can win it yet. We are learning this in real time. We are essentially building the airplane while we are already flying it.
Well, the next time you plug in your phone, just take a second to visualize that totally invisible dance. The water rushing through a massive turbine in Turkey, the wind spinning a composite blade in the North Sea, the incredibly complex math running in a server room somewhere in Paris.
And the entirely silent silicon chips deciding, microsecond by microsecond, to keep that power flowing seamlessly right to your hand.
It's the completely hidden miracle of the modern world.
It really is.
And on that thought, we'll leave you to ponder the complex physics behind your toaster. Think about a traditional power plant. Coal, gas, nuclear. It doesn't really matter what fuel you're burning. The mechanism is largely the exact same.
You burn stuff to make steam.
Right. You use heat to make steam, and that steam pushes a giant turbine.
But now we're shutting down those big thermal plants. We're replacing them with decentralized, weather-dependent renewables. And looking at the engineering specs from the sources here, solar panels do not spin.
No, they definitely do not spin. They are completely static. And wind turbines, even though they obviously spin, they are usually electronically decoupled from the actual grid frequency. They connect through things called inverters.
The inverter. Now, this seems to be both the villain and the hero of our story today.
It really is the main gateway. So an inverter is basically just a box of solid-state electronics. It takes the direct current power from a solar panel or a battery and chops it up to match the grid's alternating current wave.
Okay.
But here is the fundamental problem. Inverters have zero mass, zero weight, zero physical inertia.
So we're literally taking the shock absorbers off the car.
We are taking the shock absorbers off the car, and to make it worse, we are driving faster. As we reach 50, 60, 80% renewable penetration on the grid, we're running an inertia-starved system.
What happens in an inertia-starved grid if a line trips? Like if we hit that pothole?
You hit the cliff edge. Without that heavy iron to push back, the frequency doesn't just dip slowly like it used to, it plummets.
Wow.
We were talking about a drop that used to take maybe 10 full seconds, now happening in a fraction of a single second. It happens so fast that the mechanical safety relays, the actual physical switches, designed to protect the grid,
It can't even react in time.
can't even open in time. The whole system just collapses into a blackout.
That paints a really vivid and kind of terrifying picture. We've totally removed the physical safety net. But naturally, reading through these sources, the engineers didn't just give up. They decided to code a new safety net.
Right.
And this is where we get to the new challenger, synthetic inertia.
Yes. If physics won't give us inertia for free anymore, we basically have to manufacture it. We have to fake it.
Fake it till you make it, grid edition.
Exactly. That is what synthetic inertia is. It's an entirely manufactured phenomenon. It's an advanced control function programmed directly into the inverters of battery storage systems or solar farms.
So we are literally teaching silicon to pretend to be steel.
In a very real way, yes.
Yeah.
These advanced inverters are watching the grid frequency using incredibly high-resolution sensors. I'm talking about sampling the electrical wave thousands of times every single second.
Okay.
The instant they see the frequency start to change, the software jumps in. It calculates the rate of change of frequency, which engineers call Rokoff, and it immediately commands the battery to inject or absorb active power to stop the drop.
It sounds like it's trying to mimic the heavy rotor, but there has to be a speed difference here, right? Because you've highlighted the blistering velocity of digital assets in the research.
That is the massive advantage of code over iron. Mechanical systems are inherently bound by physical reality.
Right, things have to physically move.
Exactly. If you want a massive steam turbine to push harder, you have to mechanically open massive valves. The steam actually has to physically flow through pipes. The pressure has to build inside the chamber. All of that takes time. Seconds.
Which is an eternity when the grid is crashing.
Right. But a battery is solid-state electronics. It operates entirely in the domain of seconds and milliseconds.
So it can react significantly faster than the old mechanical systems ever could even dream of.
Much faster. They can smooth out those frequency ramps with incredible aggression. It's not just a passive shock absorber anymore. It's more like an active, computerized suspension system that senses the bump in the road and adjusts the wheel downwards before you even feel it in the driver's seat.
That sounds perfect. And there's always But in these deep dives, you've highlighted a major definition problem in the sources. Apparently, there is a lot of confusion between synthetic inertia and something called fast frequency response, or FFR.
Yes.
Now, reading the surface level, I assume they were just the exact same thing.
You and many experts in the field, actually, they're very often conflated. But the distinction is incredibly crucial for the actual engineering of the grid. Let's use a car analogy again to make this crystal clear for everyone listening.
Okay, I'm behind the wheel.
You're driving on a highway, and you have cruise control on. That cruise control system is basically fast frequency response, FFR.
Yeah.
If your speed drops from 60 miles per hour down to 55 miles per hour because of a hill, the computer notices that gap. It sees the absolute error.
It sees I'm 5 miles an hour too slow.
Right. And then it hits the gas to get you back up to 60. It acts based on the absolute deviation. It says, I am slow, therefore I must accelerate.
Okay, so FFR sees the error, I'm too slow, and it fixes it. That makes sense.
Right. But synthetic inertia is a completely different beast. Synthetic inertia is like the heavy mass of a massive freight train.
Okay.
If that massive freight train hits an uphill slope, it doesn't wait until its speedometer drops to push back. Its sheer mass actively resists the deceleration itself. It fights the actual change in speed, not just the lower number on the speedometer.
I see. So FFR is just looking at the speedometer. Well, synthetic inertia is actually feeling the deceleration. It's reacting to the rate of change, not just the final number.
That is exactly it. It reacts to the Rokoff, the rate of change of frequency. And implementing that in code is incredibly hard.
Why is it so hard? It's just math, right?
Because to know the precise rate of change in real time, you have to do calculus. You have to take the mathematical derivative of the grid signal as it's happening.
And grid signals aren't just clean, smooth lines on a graph, are they?
Not at all. They are incredibly messy. They are noisy. You have electrical static, interference from large factories turning on, maybe lightning strikes a few miles away. If you try to calculate the exact mathematical slope of a jagged, violently noisy line, your answer jumps all over the place. It's like trying to draw a perfectly smooth trend line on a stock market ticker that is violently bouncing up and down every single millisecond.
That sounds like a total recipe for disaster. If the computer reads a random noise spike and genuinely thinks it's a grid crash, it might inject a massive surge of power when it shouldn't.
Exactly. And then you add in what the engineers call the latency problem.
The delay.
Right. Physics is instant. If you push a solid brick wall, the wall pushes back immediately. But code takes time.
How much time?
Well, the sensor has to physically read the frequency, send that data to the CPU. The CPU has to run the calculus algorithm and send the command to the power electronics, and the solid-state switches have to actually open.
But we're talking milliseconds, though, right? Does that really matter in the grand scheme?
In this game, it absolutely matters.
Yeah.
The sources mention latencies ranging from 150 milliseconds to a full 2 seconds for some distributed systems.
150 milliseconds still sounds incredibly fast to me. That's literally the blink of an eye.
In human time, sure. But in grid time, it is an eternity. The alternating current wave cycles every 20 milliseconds.
Wow.
Yeah. If your synthetic power injection comes 200 milliseconds too late, you might actually push at the exact wrong moment of the wave. You could be entirely out of phase.
Meaning?
Meaning, instead of stopping the wobble, you accidentally amplify it. You could actually shake the entire grid apart with your own safety system.
That sounds absolutely terrifying. You try to save the patient, and you end up causing a fatal seizure. So how do the engineers fix that?
They use something called a sliding window method. Instead of looking at a single instantaneous data point, the software looks at a rolling window of time, say 250 milliseconds.
Okay.
And it calculates the average change over that specific window. That smooths out the curve and filters out the electrical noise. But it is always a constant, agonizing trade-off between being fast enough to catch the falling grid and slow enough to be totally accurate.
It really is the exact point where physics meets computer science. You're trying to literally code a law of physics into a chip.
You are.
Now, this brings us to the brains of the operation, as the sources call it. We have two main types of inverters discussed here, grid following and grid forming. And the sources call grid forming a massive paradigm shift. What is the actual difference between these two?
This is arguably the most important concept for the entire future of the grid. For decades, almost every single inverter installed, whether it was solar, wind, or a battery, has been a grid-following inverter.
Grid following.
Right. Their operating philosophy is basically subordinate. They are completely passive participants on the network.
They're just following the leader.
Yes. They use a device called a phase-locked loop, or a PLL. This device constantly listens to the grid's larger voltage waveform. They find the heartbeat of the big thermal plants, and they simply match it. They inject the renewable power in perfect sync with the big boys.
Okay, so what's the flaw there?
The flaw is they absolutely need a strong, stable signal to follow.
What happens if the signal gets weak or unstable?
If the grid becomes weak or chaotic, say during a massive storm or a short-circuit fault, the voltage signal gets very messy. The grid-following inverter gets completely confused.
It loses the beat.
Exactly. It suffers what engineers call a loss of lock. It can't find the rhythm anymore. So what does it do to protect itself? It immediately disconnects from the grid.
Which is exactly the exact opposite of what you want during a crisis.
Exactly. Just when the grid is begging for power the most, the grid-following inverters just quit because they lost their reference signal.
Yeah.
This dynamic can absolutely cause blackouts.
Mhm.
And that is why we have the grid-forming inverter.
The new way.
The new way. Grid-forming inverters do not follow. They lead. They don't look around for a reference signal to copy. They fundamentally create one.
How do they do that?
They synthesize their own internal voltage waveform. Basically, a perfect mathematical sine wave generated by virtual oscillator models inside the software. And they confidently push that wave out onto the grid.
I really love the water tank analogy in the research notes here. Can you walk us through that? It totally made it click for me.
Sure. Think of the entire electrical grid as a massive system of water tanks, all connected by large pipes. The physical water level represents the voltage or the frequency.
Okay.
A grid-following inverter is like a water pump that only knows how to work if the water in the pipe is already at a perfectly steady level.
Mm-hmm.
If the water level drops too low because of a leak, the pump says, I can't work like this, and it totally shuts itself off.
Totally useless in a drought.
Right. But a grid-forming inverter is completely different. It's like a giant, active, highly intelligent reservoir. It has its own pressure sensors. If the pressure in the connected pipes drops suddenly, it autonomously opens its massive valves.
It doesn't ask for permission.
No. It just immediately dumps water into the system to stabilize the pressure level before the whole system runs dry. It creates the pressure itself.
And the sources mention this creates what they call a virtual synchronous machine.
Yes. It behaves exactly like those big spinning iron generators we talked about earlier, but it does it entirely digitally. And this unlocks an absolute superpower for the grid: black start capability.
Black Start. That honestly sounds like a sci-fi movie title.
It's the holy grail of grid recovery operations.
Huh.
If the whole grid goes entirely dark, a total blackout, Grid-following inverters cannot restart it.
Because there's no signal to follow.
Exactly. They have absolutely nothing to follow. They're waiting for a heartbeat that isn't there. But a grid-forming inverter, it can wake up in the total dark, generate the reference signal from scratch, and reboot the entire dead grid piece by piece.
It can literally bring a dead grid back to life without a single spinning steam turbine.
It can.
That is just incredible. But, as with all technology, theory on paper is one thing. Real-life stress tests are another. And apparently, reading the data, the real-world proving ground for all of this isn't a lab in Silicon Valley. It's actually Australia.
South Australia specifically.
Yeah.
It is absolutely the ultimate global proving ground right now.
Why Australia?
Because they have a massive amount of renewable energy. There are days where they're generating over 140% of their entire state's demand just from wind and rooftop solar.
Wow, 140%.
Yeah, and physically, they are at the very end of a very long, very skinny transmission line. It is an extremely inertia-starved, volatile grid system. Honestly, if it works in South Australia, it will work anywhere on Earth.
And you have two specific case studies here from Australia that are just wild to read about. Let's start with case study 1, the Callide Sea explosion, May 25th, 2021.
This was a massive, incredibly destructive event. Callide Sea is a major traditional coal-fired power station up in Queensland. They were doing a totally routine upgrade on a battery charger for Unit C4.
Okay.
And something went wrong. The DC power supply suddenly failed.
Now, DC power sounds like a small thing in a massive plant, but that controls all the safety systems, right?
Exactly right. It completely knocked out the plant's protection systems. So when a subsequent electrical fault happened, the massive steam turbine, this spinning behemoth of iron, didn't trip offline to protect itself like it was designed to.
Oh, no.
It kept spinning, but it became asynchronous. It was physically fighting the grid's magnetic field. The friction in the massive bearings built up rapidly, the physical forces became totally uncontrollable, and the actual turbine literally disintegrated.
Disintegrated. The notes here say there was 300-kilogram shrapnel.
Yes. 300-kilogram chunks of solid metal were thrown violently through the physical roof of the power plant. It was a total catastrophic destruction of the generator.
That is insane.
But the physical explosion was just the very start of the nightmare. That explosion sent a massive, violent electrical shockwave racing through the entire grid. The frequency plummeted instantly. Because of that violent shock, 9 other major power plants across Queensland tripped offline immediately just to protect themselves from the surge.
The ultimate domino effect.
The cascade. Queensland was electrically separated from New South Wales. The entire region was teetering right on the brink of a total system collapse. But then, hundreds of miles away down in South Australia, the Hornsdale Power Reserve, which is the famous Tesla big battery.
This is the big digital hero moment.
It really is. It was running in virtual machine mode, that grid-forming software we just discussed. It instantly detected the frequency crash, and it injected a massive wall of power milliseconds later.
Wow.
It acted as a perfect digital shock absorber. It arrested the frequency plunge. It stopped the bleeding just long enough for the slower safety systems to shed some load and stabilize the entire grid.
So a piece of code running in a battery hundreds of miles away literally saved the grid from a mechanical explosion at a coal plant.
Precisely. It prevented a multi-state blackout.
Right.
It definitively proved that digital synthetic inertia absolutely works in the real world.
There was another major event, too, mentioned in the sources, the islanding event in November 2019.
Yes, this one really showcases the pure endurance of the technology. A severe transmission line failure physically severed South Australia from the rest of the country's grid. They became an electrical island.
Completely cut off.
Completely. And for 5 straight hours, that Hornsdale battery acted as the digital anchor for the entire state. It continuously pushed and pulled against wildly volatile frequency oscillations, keeping the entire islanded state perfectly stable until they could repair the lines and reconnect.
And the economics of that battery are staggering. The notes say it saved consumers $150 million in just 2 years.
It did. Before that battery was installed, the local gas generators held a complete monopoly on frequency control services. They charged an absolute fortune to the grid operator because they knew they're the only game in town.
Right.
The battery came online, completely crushed their monopoly with better performance, and the market price of grid stability just plummeted.
So it's safer, it's significantly faster, and it's much cheaper. Honestly, it sounds like game over. Why haven't we just replaced every power plant with giant batteries yet? Why do we still have this Achilles heel?
Because silicon has hard physical limits. We're back to the laws of physics. The one major thing silicon inverters absolutely cannot handle is brute force.
What do you mean by brute force in an electrical sense?
Fault currents. Imagine a huge lightning strike directly hits a transmission tower, or a massive tree falls across a high-voltage line. It creates a massive short circuit.
Okay.
For a split second, the grid desperately needs a massive, overwhelming surge of electrical current to essentially burn through or clear that blockage. It's like flushing a severe blockage out of a pipe using a high-pressure fire hose.
Yeah.
You absolutely need pure volume.
And the old copper and steel generators could provide that volume.
Easily. A big solid chunk of copper and steel can seamlessly surge to 6 or 7 times its normal rated current for a few seconds. It gets very hot, sure, but it has immense thermal mass. It doesn't melt.
Right.
But a tiny silicon transistor, if you try to push 6 times the normal current through a delicate silicon transistor, it doesn't just get hot, it literally vaporizes. Instantly.
It just melts down.
It violently explodes. So software engineers have to artificially limit the output of these inverters so they can survive a fault. Because of that software limit, they simply cannot provide that massive brute force kick needed to clear a major grid fault.
I see. So we essentially have the brains now, the code, but we completely lack the raw current.
Exactly. And that limitation is exactly why the true future of the grid is hybrid. We're actually seeing the massive return of a century-old technology to solve this, the synchronous condenser.
The zombie motor.
Yeah, that's a funny name for it. But essentially, yes, it's a massive, heavy electric motor, but it just spins freely. There's no steam turbine attached to it. There's no coal furnace boiling water.
So what's the point of it if it doesn't actually make any new power?
It provides the physical brawn that we lost. It provides raw mechanical inertia and short-circuit strength at thermal mass, literally just by existing and spinning on the grid.
So the ultimate solution isn't iron versus code, it's both.
Yes, it's collocation. You physically build a massive synchronous condenser and a smart grid-forming battery at the exact same location. It's a perfect engineering symbiosis.
Walk me through exactly how they work together during a major crash, like a lightning strike.
Okay. A severe fault happens, lightning hits a line.
Right.
Stage 1. The spinning condenser takes the immediate hit. It provides the brute force massive current needed to clear the fault, and it uses its physical inertia to survive that initial violent shock wave without tripping offline. It buys precious time.
Okay.
Then, stage 2. Milliseconds later, the grid-forming battery wakes up. It calculates the drop and injects massive, precise active power using synthetic inertia to restore the frequency and perfectly stabilize the recovery.
So physics buys the time for the code to actually work.
That's exactly the tagline. Physics buys time for the code. It perfectly resolves the temporal mismatch between the two technologies.
That is a fascinating engineering solution, but I really want to pivot and talk about the money aspect again. You mentioned way earlier that inertia used to just be free. It was just a happy byproduct of burning coal.
Right.
But now, with batteries and condensers, it's something we actively have to buy.
We do. And if you are a commercial battery developer, why on earth would you spend extra money to install complex grid-forming software if nobody's actually paying you for grid stability? You're in the business of selling electricity, not charity stability. So the traditional market signals are totally broken.
So how are grid operators fixing that broken market?
We basically have to invent entirely new commodities. We have to commoditize stability itself. Look at Great Britain, for example. The national grid over there launched a really innovative program called the Stability Pathfinder.
A pathfinder for stability?
Exactly. It basically went to the market and said, we will pay you millions of pounds strictly to provide inertia. We honestly do not care if you generate a single watt of usable power. We just want to buy your heaviness and your stability.
So they're literally awarding lucrative contracts for heaviness.
Literally. They awarded huge contracts for companies to build freely spinning synchronous condensers and smart grid-forming batteries just to sit there, connected to the grid, ready to stabilize it. It's officially decoupling the stability service from the actual energy generation.
And does spending all that money actually save them money in the long run?
Huge amounts. They project it will save consumers around 58 million pounds annually by 2030.
Wow, how?
Because without these standalone stability contracts, the grid operator would be forced to pay expensive, polluting gas plants to run all day long just to provide stability, even on days when the wind is blowing so hard they don't actually need the electricity.
That makes total sense. And the Texas example in the sources is really interesting too. EUR kite.
Texas is fascinating right now. They are experiencing absolutely massive wind and solar growth. And they currently have 125 gigawatts of batteries sitting in their connection queue.
125 gigawatts. That is an insane number.
It is. And they are operating in a serious danger zone.
Yeah.
In Texas, if the grid frequency drops to exactly 59.3 hertz, automatic load shedding triggers. Blackouts begin.
Right.
They did a massive simulation study showing that digital battery assets programmed with really aggressive droop settings, let's say a 1% droop, can arrest frequency decline significantly faster than sluggish old thermal plants, which usually operate with a very slow 5% droop.
Droop. That's a fun word. What does that actually mean?
Yeah, it's pure engineer speak for sensitivity. A lower droop percentage means a much higher sensitivity to frequency changes. The Texas study showed definitively that by relying on these hyper-fast, highly sensitive batteries, ERCOT could actually reduce its total critical inertia requirement for the whole state from 94 gigawatt seconds down to just 71 gigawatt seconds.
That's a massive efficiency gain for the whole market. So the engineering is clearly solving the physical problem. The economics and the markets are finally catching up. But then we hit section 7 of your research, the hidden danger.
Yeah, this is where the whole story takes a pretty dark turn.
Cybersecurity.
We are fundamentally transitioning the grid from unhackable physics to highly hackable code.
Explain that transition for me.
Well, a 500-ton spinning steel rotor inside a coal plant cannot be hacked by a computer virus.
Right, obviously.
You can't send malware to a solid chunk of steel. It simply obeys Newton's laws of physics. But a modern smart inverter. It is literally an Internet of Things device. It is constantly connected to the Internet for remote software updates, market data, and central control.
And if it's connected to the internet, it's inherently vulnerable. What are the actual attack scenarios we are worried about here?
They are chilling, quite honestly. The most dangerous one the researchers highlight is called false data injection. Remember how synthetic inertia works? It calculates the rate of change entirely based on what its external sensors see.
Right. It reacts instantly to the data it's fed.
So imagine a hostile state actor or a hacker gets into the inverter software. They feed it spoofed, completely false data. They tell the inverter, hey, the grid frequency is absolutely skyrocketing right now. It's way too high.
Oh, so the inverter naturally tries to apply the brakes.
Exactly. The inverter thinks, I need to lower this dangerous frequency immediately, so it starts absorbing massive amounts of power from the grid to act as a brake.
Right.
But in physical reality, the grid was totally fine.
Right.
By absorbing all that power suddenly, the hacked inverter actually causes the collapse. It literally creates the exact massive emergency it falsely thought it was solving.
It's a self-fulfilling prophecy triggered completely by a lie.
And if a hacker does this to thousands of connected inverters all at the exact same time, say a huge fleet of residential rooftop solar panels or smart EV chargers parked in people's garages, you could trigger a massive, highly coordinated blackout that the central grid operators wouldn't even see coming until the lights went out.
That is wild. Or the sources also mention a denial of service attack, just blinding the control room entirely.
Right. Or hijacking, where hackers slowly force the inverters to inject the wrong type of reactive power to slowly destabilize the local voltage over hours or days. It's like a slow, invisible poison in the local grid.
So how on earth do we actually defend against this? I mean, if the code is the weapon now, does the code also have to be the shield?
It absolutely has to be. Human operators are way too slow. You can't just have a guy sitting in a control room checking for hackers when the attack executes in literally 20 milliseconds. We need AI versus AI.
Artificial intelligence living inside the actual inverter.
Yes. Engineers are now using advanced machine learning, specifically things called long short-term memory neural networks, and they are embedding them directly right onto the silicon chip of the inverter itself.
What does that AI actually do on the chip?
It constantly learns the unique, localized fingerprint of the physical grid. It knows exactly what a real physical lightning strike looks like in the messy electrical data. It intimately knows the local physics. And crucially, it knows exactly what a clean digital spoof looks like.
So it can essentially spot the fake data.
Yes. The latest research shows this embedded AI can successfully distinguish between a real physical grid fault and a malicious digital spoof attack with over 90% accuracy in real time.
That is incredibly impressive.
It is. So if the onboard AI suddenly sees a frequency signal that looks artificially wrong, it can instantaneously override the master command. He says, no, that data is fake. I am isolating myself, and it cuts the hacker off entirely before the damage can spread to the wider grid.
Wow, it's like an autonomous immune system for the power grid.
That's a really great way to put it. And we're seeing aggressive legislative action, too. Lithuania, for example, recently passed laws outright banning remote internet access on certain high-risk grid inverters. They're taking this vulnerability incredibly seriously.
It is absolutely fascinating. I mean, we started this conversation talking about heavy metal spinning in a boiler room, and we've somehow ended up discussing neural networks fighting state-sponsored hackers on a microscopic silicon chip.
It really highlights how the grid is now a socio-technical complex system. It's not just a dumb machine anymore. It's a blend of raw economics, advanced code, immutable physics, and national security.
So bringing this all together as we wrap up, what is the final verdict here? Can we actually do this? Can we reliably run a giant continent-spanning civilization on code?
The verdict is yes, we absolutely can. The digital response, like we saw in Australia at Hornsdale, it undeniably works. It's faster, it's far more precise, and frankly, it's capable of complex maneuvers that mechanical systems never even dreamed of. But, and it's a massive but, we cannot recklessly abandon physics.
We need the dance between the two.
We need the dance. A carefully choreographed dance between the iron and the code. We will need the synchronous condensers for the raw brute force survival, and the grid-forming inverters for the blinding speed and finesse. It's not a hostile takeover by silicon, it's a mandatory partnership.
And as we look to the future, it really seems like the main challenge isn't just physically building it anymore.
No. The primary question isn't just, can we build it? We already know we can build it. The truly terrifying question is, can we secure it? We are actively trading the dumb, unbreakable stability of sheer weight for the incredibly fast stability of intelligence. And the problem is, intelligence can always be deceived.
That is a deeply provocative thought to leave everyone with. We are moving from a world stabilized by the sheer unthinking weight of iron to one stabilized by the brilliant intelligence of algorithms. But as we make the grid smarter, we inadvertently make it exponentially more fragile to human malice. It's a brave new world, and it's being coded literally as we speak.
It certainly is.
Thank you so much for taking us through this incredibly complex deep dive. Honestly, it has completely changed the way I look at the power lines outside my window.
My pleasure. Thanks for having me.
And a huge thank you to you, the listener, for plugging in and exploring this with us. There's always more beneath the surface. We will catch you on the next deep dive. Stay stable out there.